Yay, data! Here we go. Let's begin. All right, we're going to look at how inferential statistics can look at the associations between two variables. So first off, we have x and y variable. I'm just going to get to the next one. Oh, it cancels it out. Okay, so let's start off with our y variable, and that's going to be our dependent variable, and also known as like a response variable. So what ends up happening after we examine based on our independent variable. Our independent variable is going to be our x, and that's going to be our explanatory variable. So, for example, historically, if we take a data set where there were 11 countries and our X, we would want to look at our cigarette consumption among those 11 countries. And the response would be the lung cancer mortality per 100,000. So, in other words, we are wanting to know basically what the cigarette consumption, how that can explain our response variable of lung cancer. So again, lung cancer would be this response of like, okay, well, how much of an association is there between smoking cigarettes and lung cancer? It kind of seems common sense now, but it wasn't that long ago when it wasn't common sense. All right. So again, we have our explanatory. There's different names for this. We have X, and we'll see X more when we work with regression the following week. We have our independent variable. We have factor, treatment, and exposure. And then on the other side would be the responses to those. So for X, it would be Y. For our independent variable, it would be our dependent variable. For our factor, it would be an outcome. For a treatment, it would be the response. For an exposure, it would be a disease. And that's going to be our focus today, is correlations. We are going to go over two primary focuses of correlations. We're going to look at scatter plots and then the actual correlation itself. That said, when we are looking at this, we are looking at the relationship between two continuous variables. Okay, so let's just backtrack to what we have done so far. Chi-square was looking at the association between categorical variables to another set of categorical variables. We rewind a little bit more. We are looking at categorical variables as our independent, and we are looking at a scale or continuous as our dependent variable. So going back to my classic one that I'm just going to use is that I'm wanting to look at gender. That would be a categorical, because I basically can put those into boxes, and then we're going to look at the scale of loneliness scale. Okay, and so that's the continuous. So within this, though, within testing of association, where a correlation is going to come in, that we're going to both the dependent and independent variable are going to be scale. So within our parametric test, we use a bivariate Pearson's correlation coefficient. When it's non-parametric, we use a Spearman's correlation coefficient. And then we also have partial correlation. We'll get to all of that. All right, so first off, let's talk about this top one, this bivariate Pearson's correlation coefficient. So again, we're looking at the relationship between two continuous variables. So this is also known as Pearson's correlation, Pearson's product momentum correlation, and the Pearson correlation produces a sample correlation coefficient of R. We're going to see R a lot, and this is going to basically be our measurement for this. And this will show the measurement of strength and the direction of the relationship between the pairs of continuous variables. So with the Pearson correlation, this evaluates where there is statistical evidence for a linear relationship. So do those two variables actually have some sort of relationship to them? And among that, the same pairs can be focused around the population, and this can be represented by a row. We're not going to get too much into that because we just want to play with data when it comes to how do we correlate between variables. All right, A bivariate correlation, just some things to note with it, that they cannot address nonlinear relationships or relationships with categorical. So this is just going back to what I just started off with, and that is saying there are no categorical variables in this. That's it. Correlation is just looking at continuous and continuous. I'll give an example right off the top of my head, and these are the simple ones, right? This is scale to scale. I am looking at height and I am looking at age. Both of those are scales. Is there a relationship between height and age? Probably, most likely not, right? Okay, but that gives you an idea of the way that you can assess things. There are no categories to put into boxes. So the bivariate Pearson correlation looks at this as an association among these continuous variables. And they don't necessarily provide an inference about causation, no matter how large it is. So you'll hear this a lot. Correlation does not mean causation. It's said tons of times, and you will hear it. That just because something is correlated doesn't mean that it's caused that way. And we have some examples to go about this, so you can see how you might use it at your next party. I don't know. Okay, so the bivariate correlation, we are looking at the linear relationship that exists between two variables, and this is found through the correlation coefficient of R. And the R is going to be a number that is between -1 and +1. And and so it can be 0. And so if the correlation, if the R ends up being closer to -1, let's say it's -9.87, then that means that there is a very strong negative correlation. Whereas if it was, say, a positive, a 0.2, well, that would be a very, very weak positive correlation. We really wouldn't consider that a correlation much. But there's always going to be a number that's associated with a correlation. And so, yeah, if you get closer to 0, then that is representing a weaker relationship. So can go either decreasing or increasing. So here are 6 examples that we can look at. So starting with the top left, this is a perfect positive correlation. It is a 1, and you can just see that everything is just in a nice linear fashion. It's like being in line at... being in line. I'm just going to say that. I don't want to promote any particular business. All right, and then here's a negative correlation. So notice that it is going down. So we always go from left to right, and so therefore it starts up at the top and then it goes down as you increase on the x-axis. So again, a way that we can look at this with an x and y is that with a positive relationship or positive correlation, as the x-axis increases, the y value increases, whereas as with a negative correlation, as the x value increases, the y value decreases. All right, so here is some visual representations of what a 0.9 R looks like. So it's a little bit more scattered. Here's a 0.5. So you notice that it's starting to disperse. So it's harder to say that there actually is an association. There is some guidance of, that x and y relationship, but it's really obviously not as strong. And here they are both in a negative form. Okay. So correlational strength refers to the degree to which points adhere to this trend line. That's what we were just looking at. We've said it before, don't always trust it from the eye. We need to actually get some true information. So here's an example right here. So the left plot, this one shows a much weaker correlation than the right plot. And you can look at that, yes, that you can see an idea of as the x value increases, so does the y, but it is much more scattered everywhere. And so that's something to take in consideration when you're looking at something visually. However, this is the exact same thing It's just zoomed in. So we can see just based on what numbers we put into our graphs is going to show up something different. I think what would be a good exercise is to actually use something as simple as one of the softwares that are available to us, and just to play around with how you can manipulate how a graph actually looks. This looks like highly scattered, right? It almost caught me off guard before I read it and then had to remind myself what we're looking at here. And then I look over here, and yes, this is the exact same thing, same numbers and everything. It's just that what we have here are ranges of numbers show up something different. Again, don't trust the eyes. Sometimes. All right. So we always need some conditions or assumptions, going back to the bouncer idea. That is the condition or the assumption of how we are going to move forward with an analysis. So condition or assumption number one is that you need to have two or more continuous variables. So this can be an interval or a ratio. What that's saying is, there can be a 0 in there. It can go like to you can add some decimal or a decimal place, and then it can go on for a long time. So again, scale, continuous, quantitative. So many words, I know. So let's just use with what this is saying is continuous variables. For instance, right here, let's check if we meet the first assumption. Are both of these continuous? Yes, they are. These are not anything that we are putting into boxes. All right, next, cases that, our second assumption is that cases that have values on both variables. So yes, there are values for both variables throughout all of the observations. And then 3, that there's a linear relationship between the variables. We'll go further into that. Because linear relationships can also look very different. So for instance, this is a linear relationship. It starts off at one point, and you can clearly see that there is a nice little, it's like an arc. So you can see visually that there is some sort of linear time here, but when we actually plug this into the numbers, we get an R of 0. And you can actually see this because it's actually symmetrical. So basically what you could see is that this dot cancels this dot out, and so on and so forth. So decent example, just to give you an idea of just because you see a line doesn't mean that there's a relationship. That's all we're saying. All right, so here's some more examples of linear relationships. Okay, going back to the assumptions. So we met our first 3 assumptions with at least that example. So let's go a little bit further with it. So these need to be independent cases. So in other words, that each of the observations must not be the same. So going back to this example, we can't have Switzerland twice here. That's basically what we're saying, is that all of these have to be independent of one another, especially within the variables. So we can look at cigarettes in the 1930s, and then cigarettes in the 1931. Well, you could, because that's 2 different time frames. However, those are independent of each other. So they just cannot be dependent. So they have to be, again, unrelated. And they also can't influence one another. So if we were looking at, a 1930 and then a 1931, we wouldn't be doing a correlation, actually. We would be doing a pre-post or a paired sample t-test. All right? And the bivariate correlation coefficient and the corresponding significance test are not robust when these independents, like if you have more of a dependence between the 2 variables, it's not going to be as robust. So basically what we're saying is they should be as independent as possible. Independent variables. All right, our 5th assumption or condition is that each pair of the variables, that there should be some normality. Okay, so that means that they make a nice bell curve for both of the variables. That has been common throughout basically our entire practice, except for like a chi-square and, and with like the t-test and the assumption or the ANOVAs, we test those assumptions, and we know that, oh, we can't run an independent t-test. We have to use a non-parametric. So we have to make sure that we're moving forward with it. So they both have to be normally distributed, and R can still be used descriptively when the data are not normal. So you can still provide an R, but you need to express that these are not normally distributed. Here is a visual of what this would look like. Okay, and so we have two more assumptions for this. So again, they need to be random. We're kind of just like digging back to all of the original things that we talked about at the beginning of the semester, right? And then of course, no outliers. We don't want any outliers on this. Here's an example of if you have an outlier with a correlation. So again, if you have an R of 1, that is like a perfect linear relationship in correlation, right? So this is actually showing, if you were to plug these in, you would get an R of 0.82. That's very high, very close to 1, in fact. However, it's because of this one little outlier that makes this 0.82, because it's just so extraordinary out there. Right, so we want to make sure that there are no outliers. Be a little bit more hesitant when you do have those outliers. So let's go ahead and practice the hypothesis testing steps. So first we need to state the problem, then we go to the null alternative and alternative hypothesis. We calculate that test statistic, the P and interpretation, the significance and the alpha, and then we state the conclusion. So all of these things, we know how we're doing it. All right, going back to our original example, that is there an association or correlation, same thing, between smoking and lung cancer rates? So we are using the smoking as our X, as our explanatory variable, and we are using lung cancer as our Y, or response variable. All right, so here are the 11 countries. And let's just look at the data real quick. So we have 11, we have down at the bottom with the least amount of smokers and lung cancer is actually Iceland. And then who is up at the top? USA, USA, of course, we made it to the top. Way to go, us. All right. So we will look at the null and alternative hypothesis. So you would state that for the null hypothesis, that there's no relationship between smoking and lung cancer rates. Whereas the alternative is that there is a relationship between the smoking and lung cancer rates, that there is an association with the amount of smokers that you have and the amount of people with lung cancer. So we're going to open up DAL equal first off, all right? So I am actually going to go through it within the presentation on this. It's very hard for me to go back and forth on my particular computer. Maybe I might be able to pull it off, but I want to go through it on the PowerPoint presentation first. Okay, so the first thing that we want to do is do a scatter plot. Let's see what we actually get and what it looks like. So you're going to go to Graphs, Legacy Dialogues, and then down to Scatter-Dot. We're going to choose this scatter dot. We're going to define. And then we are going to put in, for our Y, we're going to put the lung cancer mortality. And then within the X, we are going to do the cigarette consumption. And then we would put the markers based on the country. So that way, I haven't tested this one out, and it's been a while since I've done this. So if you don't label it, then I actually question what it shows. So this is like a good example of, why to have, certain, nominal variables just to like categorize what you're actually looking at, especially for something like this example. All right, so once we have all that set up, hit OK, and what do we got? Well, it looks like, actually, you know what this looks like? I don't know if you were a kid and you had like one of those, like, it was filled with water and those little like rings, and then you press the button and it would just push the water, with some air, and then you get those little rings onto little spots. I don't know why my mind went there. Fine, let's just call these Fruit Loops. We have Fruit Loops to represent the associations of the scatter plot of countries with lung cancer rates and mortality rates of that lung cancer and cigarette smoking. Sorry, my bad. So here it is visually. We can see a bit of a of a relationship here, at least especially at the beginning with some of those lower smoking rates. But then when we get to, for instance, the United States, we definitely have more cigarette consumption. But what kind of beats us in lung mortality rates is what looks like maybe Great Britain and Finland. Okay, so we did that visually. That's nice. That's a good visual check. Next, we need to actually look at the numbers. So we would go to our descriptives and explore. We always do explore. We use plots, and this is where we're going to use a histogram, right? All right, so we've used it in the past. It's totally fine if you didn't, but now let's do it now because both of these are quantitative or scale. So we want to see what these look like. We do our normality plots with tests. All right, so here's our cigarette consumption for 1930, and then here's our lung cancer mortality rate per 100,000. And that is in 1950. I actually missed that part, that this was actually 1950. Whoops. All right, we're moving forward. All right, so when you're looking at skewness and kurtosis, they should be as close to 0 as possible. I've mentioned that previously. So the higher away, the further away this skewness number is from 0, as well as kurtosis, then the more skewness that you have within it. So if you like, you can always divide the skewness by the standard error. And if it's below 1.96, that magic number, what is that? That's 2 standard deviations away from the mean. Then we don't want it to be above or below that. Sorry, let me say that again. If we divide 0.995 divided by 0.661, and it is less than 1.96, good. It's more normal than it's normal. We want that. If it's over 1.96, or say less than negative 0.196, then it's like, oh, that's a little bit too skewed for my taste. That's what we're looking at. You can do these for both variables. Okay, so here's the formula for R. And I'm, again, not making you memorize this, but it is 1 divided by n minus 1 times the sum of all of the z-scores of the x's and the y's. Saying all of this just to know, like, this is basically the way that we find our number. This is the equation. A TI-83 could probably do one of these. Actually, I'm 100% positive that they can. Okay, so in order to find correlations, we go to Analyze, Correlate, Bivariate, and we are going to drag or just click over the cigarette consumption and then the lung cancer mortality rate. So just to point this out, I think it's important, and I need to double check that this is the way it works, but start off with your X and then your Y. So here we have our explanatory variable, which is our cigarette consumption, followed by the lung cancer mortality rate. All right. So, and what we're saying here is also the relationship is going to, it doesn't matter whether you put one or the other, but I like to do it X and Y first. Sorry, I should make that totally clear. It doesn't matter. The R is still going to be the same whichever way. It's more or less for your brain to kind of repeat the same steps over and over again the same way. That's where I was trying to keep some continuity by saying, putting my X here first and then the Y here second. All right, so we're going to hit Pearson correlation. We want a two-tailed, and we hit OK. And this is what we get. We get our R. This is our R right here, our R. This is our correlation. And so this is what's measuring the strength or the association between the two variables. So looking at this, we can say that there's a strong relationship between the two variables. When we add in the significance, our p-value, then we can actually say there's a statistically significant relationship between smoking and lung cancer. So the significance level is often misinterpreted. It does not indicate how strongly the two variables are associated. This is not testing the association. This is just testing, it's using our test statistic to determine statistical significance between the variables. So it's basically saying, wow, the probability of just this happening by chance is really, really rare. So this is awesome to see. Like, I shouldn't say awesome because then it's just kind of edifying the idea that smoking kills, right? Well, it's on boxes now. But the idea is that for as a researcher, this is really good because this determines our case is that there is statistical significance, and based on our R, that there is a strong correlation or association. Okay, so here's where we say, here's where we divide whether we're saying a weak association, moderate, strong, or very strong. So if it's less than 3, and okay, so mind you, we have a like down the middle, we have the 0, and then we can talk about all the negatives and all the positives. If I have been saying just the positives, always kind of mirror that with the negatives. So if our R is negative 0.29, we can say that that's a negative, or that is a weak negative association, right? So then we have, if it's 0.3, we can say it's a weak positive association. All right, so then we go up to our moderate, and that would lead us up to that 0.5 or negative 0.5. And then our strong would be between that 0.5 and 0.9. And then we only use the very strong, with that last 0.9 to the actual 1.0, or the negative 0.9 to the negative 1.0. So based on our last answer of 0.737, we could say that there is a strong relationship, a strong association. And this is how we would want to put it. We put our R, and what's also common is to see R squared, and this is used a lot to better look at it visually. So what this is saying is that when you multiply R on itself, which is R squared, so we would have 0.54, we would say that 54% of the variance in Y is explained by X. So in other words, 54% of the variance of lung cancer mortality rate is explained by the cigarette consumption based on our data. All right, this is like an extra part just to look at it, the effect size, and looking at R, and just knowing how to say it's much larger in the strength of the relationship versus a medium or typical. And so we have a conclusion that with a p-value of 0.1, that is definitely below our alpha. So we can say that there is a strong positive relationship between smoking and lung cancer rates. Okay, and then I put this as a note. So this is kind of like the way that you would want to put it, say, in your exam. In your exam or within your project as well. Okay, so we're going to look at the same data set, and we're going to take it into a non-parametric test. So we're basically saying that these are no longer scales, but they're actually in an ordinal way, so that they're actually being ranked rather in this kind of a fluid motion that a scale scale variable could be in. So as the values of one variable increases, the other should also increase. That's the idea of having a scale, starting low and then going high, or going high and then starting high and then going low. So we are going to find rho within that by ranking the data. So within first, second, third, fourth, and that goes up the line. Okay, so for doing that, again, we're going to do the same thing. Go to correlate by Bivariate. And then you should already have this within your variables, and then we're going to hit Spearman. So this is more widely known as like the Spearman's rank, and this looks at variables when they are ordinal. So once you calculate it, you find out, voila, you have an even stronger association and even more significance within that strength. So that's great to see. All right, and then we're actually going to skip on that part. And then now let's go to partial correlation. So this is, again, we need to remind ourselves that correlation does not necessarily mean causation. And we should always be mindful of lurking or confounding variables. And so, yeah, we have a near perfect negative correlation. Yeah, negative 0.987 was seen between cholera mortality and elevation above sea level during the 19th century epidemic. Okay, so we know that cholera is transmitted by water. And so what they were thinking is, is there a relationship of like, oh, the further away from sea level you are, the cleaner you are, the less sick you're going to get. So the people down by the beach, they're going to get the cholera because they're at lower elevation. That's kind of what the assumption is. But it was observed that cholera, so the observed relationship between cholera and elevation was confounded by a Lurkin variable. And that Lurkin variable is that the polluted water. So in other words, it wasn't the rising sea level, or what, it wasn't the elevation, but it was because people were dumping their stuff into a river and it was going downstream. And so the people who were downstream were more likely to get sick because they're drinking the nasty water. In fact, there is another term for cholera for those academics. So if you are an academic and you get you drink bad water, it's actually, you get scholera. All right, moving forward. Okay, so here is a visual of looking at that negative, that's hard, sounds weird. Negative 0.987, here it is. So as the elevation increases, then the cholera mortality rate decreases. All right, so negative correlation there. So we are going to look at this partial correlation, and this will allow us to explore the relationship between these two continuous variables and the effect of one another. So in order for this requires 3 continuous variables. So this is basically, since we're adding another variable, it's not going to say fully that there's correlation between just 2, but now we're adding in that third. That's what's also adding to this idea of partial correlation. So we're going to open up stress.sav, go to partial, it's right under bivariate, options, 0 order correlations, and then exclude cases pairwise. And then what we end up getting, this is the output, and what we have here is a pretty weak correlation, but it is statistically significant. So by the way, and this is going to be the same thing, it's just flipped on its head. So because there is just a weak association, it's significantly weak, in fact. That's how we can actually say what our findings are here. And that's it for the day. We'll do this in class.